How to reconstruct the full volume. Until now, we have only been reconstructing small fractions of the dataset, but at some point you want to reconstruct everything. And in this tutorial, first I'm going to show you the different ways of reconstructing memory or disk. I'm also going to talk about precision of the data and file formats. And finally, I'm going to show you how to do these reconstructions in Murex. So the first question is reconstruct to memory or to disk. As you have seen until now, you reconstruct your data in memory, which gives you the possibility to be interactive. You can set all your gray levels and crop and everything. You can see what's happening. And that's very efficient for small data sets. But at some point, you will come into hardware limitations. You don't have sufficient memory. And the other thing is that if you don't save the data, you will lose it when you close the application, or in unfortunate cases, maybe it even crash. On disk, on the other hand, you have an operation which is very efficient for large data set. The slices are saved immediately, and you can also script the processing, and in that way you can reconstruct several datasets with more or less the same settings. But the disadvantage, of course, is there is no interaction, so you have to know what you're doing. So mostly there is the workflow. You start reconstructing to memory, and when you have set everything you want, then you reconstruct to disk to do the full dataset. As an example of memory usage, we have example 1, where we have 375 projections, 1K by 1K, gives you roughly 5.5 gigabytes of RAM to keep everything in memory. The other case is when you have 1125 projections and 2K by 2K images, then all of a sudden you are almost at 35 gigabytes of RAM. And it's not really many computers that have that, particularly not laptops if you want to be on the move, or normal office computers. They don't have this amount of RAM. What Murex is doing is actually that it's trying to handle this problem by only reconstructing 32 slice batches, and with that you will save a lot of memory. So instead of these 1.57 gigabytes and the 18.8 gigabytes, you only have some 100 megabytes active in memory for the slices. And also this part is reduced radically. So you can actually reconstruct very large data sets without the need to have a lot of memory. Murex was actually developed on a 2 gigabyte computer, and it worked without a problem. So it is actually possible to reconstruct large data sets also with Murex. When we come to data precision, that is when we want to save the data. You can select between 8 bits, 16 bits and 32 bits float. And this tells how many bytes you will need to save each pixel. 8 bits, relatively small, but also the dynamics is not very good. So mostly you only use the 8 bits for presentation or segmented data. The 16 bits, moderate size, can have 65,000 gray levels, and it's often used for raw data acquisition or for image processing intermediate storage. The 32-bit float requires 4 bytes per pixel, but the advantage is it uses real numbers. So you don't have to do any scaling to get to the attenuation coefficients that are reconstructed. And if you want to do analysis based on the attenuation coefficients, you may consider doing 32-bit storage. On the other hand, you can also save some space by using 16 bits, but then you have to remember the scaling factors that we use to create these 16 bits. When we come to file formats, there are many file formats out there, and the most common ones that you see more or less daily are JPEG and TIFF. JPEG is something I don't recommend for scientific purpose. You can have it as for the end results in a presentation, but never if you want to do any analysis. TIFF is a very multi-purpose data format where you can put essentially everything. You can put slices, you can do volumes up to the size of 2 gigabytes. It does offer compression, but usually I try to avoid it because it just takes a lot of time and the space gain you have is not that much. So it's easier to actually work without compression. Interoperability is pretty good. Most software can handle TIFF, so that's also good. And for scientific purpose, it's a great format. You can have, you can store floating point, you can store down to 1-bit images. So you have a very big flexibility in the TIFF format. FITS is a format that was produced for astronomy, and some cameras actually store this format. It's good in the sense that the metadata is written in human readable form. And then afterwards comes the image, which you usually can't read by looking at it. FITS can handle pretty large images. Can also have multi-frame, so you can handle volumes. It handles also compression in the same way as TIFF, but again, I don't recommend it. FITS is not so known out there, so you can't, for example, in your file browser, just double click on a FITS image and it opens automatically in a viewer. If you have made a connection, for example, with ImageJ, ImageJ would pop up and open it because ImageJ can actually read the FITS. It's made for scientific purposes, so that's a good one. Nexus is a new format that currently is under discussion for use within neutron imaging. It's actually a data format that is made for large-scale facility data. It's based on a format called HDF5, and it can handle huge data files. It can even up to a terabyte if you want to work with that. Compression again is non-destructive, but also again the question is if it's worth the hustle to work with compression. Nexus is a little bit harder to work with. So you can read it in scripts. Some software can use it. This is something we are working on right now to open up more applications that can really work with Nexus. Murex can actually read some Nexus flavors, but we are still in the development phase of working with Nexus. And of course, it's a scientific data format, so this is good. And next thing I'm going to show you is in Murex. Now we have some reconstruction here, and in the first tutorial I showed you that you can say, when you have reconstructed something, in this case I've reconstructed this blue region here, then you can just click browse here, and then you can select where you want to save it. So for example in Recon, open, and it gives you the path, and then you can save something here, say slab or something. And then you can select here which data format, and as you can see, you can actually save it in 8-bit, 16-bit and 32-bit floating point. And you can also do multi-frame. That will mean one single file for all slices. It can be beneficial to work with single files, because then you have less files to work with. And the advantage is that the copying overhead and opening overhead is reduced, and then you have more faster workflow. Down here we have some nexus already, but it's still experimental and it's not actually using the format that it should. One thing is when you save it in 8-bit or 16-bit is that you have to set the grayscale interval to be sure that you actually have all gray levels covered. And in this case, from the previous tutorial, we came up with these settings, which make sense. And then you can just press Save Matrix, and in this Recon folder, you can see that we have saved the slab data. Now I'm actually going to erase this because we don't need it. Also this is not needed. So, and now if we want to reconstruct everything, then we can go over here and say we want to reconstruct from, let's see what we had, from slice 5 till slice 870, and go in here, 5 till 870, and then you can see down here an approximate memory usage, and in this case I have set the system max to 8 gigabytes, so that would actually be okay. But if you have a larger data set, then you should actually go rather to reconstruct and reconstruct to disk, and you get this dialog, and there's a warning text that you can't interact with the data, so be sure that everything is okay. And then you have to tell where to save it, so let's save it as wood. And the number of these signs tells you how much zero padding you do. So in this case I could do 10,000 images in this stack, which is well sufficient. Then I click here, reconstruct all slices, and click OK. And then it starts reconstructing. This will take a little while, so let's just wait for it. And then the reconstruction was ended, and we can take a look into this folder, and we can see that we got all the slices all the way from 5 till 869. And if we click on them, you can see the contents of each slice. And well, that would be it. We could also now, for example, open image J and take a look at the data if we would like to. And because now the interaction in this window here doesn't work anymore. So let's open the folder in image J. Just drag the whole folder. And then it says if you want to open many files as a stack, and yes, we want, then you can take a look at the whole image as it comes through here. You can also press the play button and see how it goes through the dataset. A trick here in image J is that you can also use, let's just close that one, image, stack, and orthogonal views. Then you can see what the image looks like in the different cut planes. And now let's make it a little bit smaller. Let's see, it's minus, minus, minus. And here also minus, minus, minus. And this one minus, minus. And then you can see what this image looks like in the two cut planes. And you can click around here and you can move in different places in the image. This is already a little preview to the visualization tutorial that will be coming soon. So with that, I think we are at the end of this tutorial, and thank you for listening.